giving you some time to write. So I said, recall, we were talking about improper integrals. Well, what are they? One is interval is infinite, which is type 1. And then f has a discontinuity in the finite interval, which is type 2. What kind of discontinuity? Not jump, but it's got an asymptote. Or I don't want to say this, but for us, it is okay if we say that. So I'm going to say non-removable discontinuity. The question is, how do I compute this integral? And the answer is take the limit of the proper integral. And I'm going to write proper in quotes, meaning we're going to put a constant b. And for type 1, b either approaches infinity, b approaches negative infinity, or b approaches a certain a from the right or the left. So the idea is you're taking limit. And because you're taking limit, this limit may be a finite number, or it may be infinity, or does not exist. If it is a finite number, then we say integral, which is I, is convergent. If it's infinity or does not exist, we say it's divergent. So I'm going to pause and let you write and just give me an indication when you're ready. And any questions you have. So this is what we've done. This is what your homework was. I just want you to, if I want to add something, I'm going to say these are these kind of intervals. And I'm just talking about the infinite interval. So I'm just going to pause here. So when I say questions, I help. Current B is the one that, if you are going to put B, you're going to put B because you're just going to put a constant, because in first case, you're saying, oh, the interval is infinite. That means I'm starting at A. I'm going to go back here. So I'm starting at A and approaching infinity. I can't do that infinity. So I'm going to replace infinity with some B and take the limit as B approaches infinity. So I don't know what you mean by B can be any variable. I'm just going to interpret that instead of B, can I use K for current? Yes, go for it. So you can say integral A to K and limit as K approaches infinity. Just don't use X and Y. I don't think we have. Do we have people whose name begin with X? I don't think so. Not in this class. So avoid X, Y, T's. In other words, avoid the variable used for the function itself, and then use any letter you want. So everybody ready for the next one? And any questions from the homework that you sort of looked at on this one? Okay, Bonnie, so here we go. So here's my first example for today. So it looks like, and I think before the example, I'm going to just start kind of putting it all together. So it looks like first on the final or the test, I have to check if it is a proper integral or improper integral. What do we mean by proper? Oh, everything is fine. It's integral A to B f of x dx. This is a constant. This is a constant. And f is continuous in that interval. What happens after or before, who cares? Improper, I'm going to go refer back again. So for improper, go all the way up back. This is what I'm talking about. But what I'm trying to say is this, that if it is improper, then the question is whether it is convergent or divergent. If it is proper, then I know I'm going to get a number here. This is net area under the curve. Or the volume, depending on how you set it up. But notice we're talking about proper integrals. We are talking about definite integrals in both cases. So I want to see the connection. That we are talking about definite integrals here. So we're not talking about the antiderivatives. Having said that, now here's my first example. So here's the example. We never did this. And I'm going to... So I want to come back and say this. So to integrate in both the cases, it's all going to be the techniques of integration that I have learned before. The only difference, I've got to take a limit after I integrate, and in this case, I just get a number. I don't have to integrate. Having said that, this is the question for you. It's from negative infinity to infinity. So is this a proper or improper integral? And you can say, you can type. Very good. And now I'm just going to say this, but you have an improper integral where both the ends are infinite. So my question to you is, what do we do now?
Can you split the integral?
Very good, sir. And how do we split it?
I believe it'd be negative infinity to 0, and then minus 0 to infinity.
So negative infinity to 0 and 0 to infinity. So now you're saying, okay, negative infinity to infinity, y cubed minus 3y squared dy is negative infinity to 0, y cubed minus 3y squared dy plus, and before doing the integrals, we're going to talk about something else, 0 to infinity, y cubed minus 3y squared dy. Right, this is just from properties of integrals. So stop writing, and my question to you, if one of them, one of these, either this one or this one, is divergent, what can you say about this guy? Very good, Karan. And it's divergent. Why? Because what does divergent mean? Either the limit does not exist, or it is plus or minus infinity, or it's infinity. Let's put it like that. So if it is that, so if one of them is infinity, does it matter if this was convergent or divergent? Does it matter that this adds up to a finite number? Because again, the same thing, isn't it? If you have infinite amounts of money and just you add $2 more to it, it doesn't make any difference. You still have infinite amount of money, which means the integral is still divergent. So when I see integrals like this, or intervals like this, the first thing, split it up. Second thing, I would just go ahead and compute one of those integrals. And that shows if one of them turns out to be divergent. I think I want to make a flowchart. So here we go. So compute one of those. If one of those turns out to be divergent, then stop, integral is divergent. If one of them turns out to be convergent, then no, you have to continue, compute the other one. And then add the two. So my question to you, should we be finishing this or we all right? Because the integral itself is not too bad. It's just y cubed minus 3y squared. So my question to you is, should we be finishing this or we are all right then? Okay. So the rest of you, I'm going to assume that you are with Karan and it's okay.
I just have one question, which is you would just substitute infinity with b and
Correct.
solve the integral and see if it came out with a number or infinity and does not exist.
Correct.
Right. All right,
Yeah.
then I'm fine.
Okay. So you would just need to carry out that integral. If it turns out to be infinity, then as I said, you are here, you stop, you're going to say, okay, one part is infinity, so I don't even have to go back the other one. If not, you are going to continue and compute both bits. So I'm just going to, so there is a theorem in this section that we have to do, which I like to do because it matches up very, very well with sequences and series that we are going to do here. So there's one important result here. So I'm going to write that result down. And it's going to be from last lecture. So here we go. So last lecture. What did we see? Oh, we saw that integral 1 to infinity 1 over x squared dx was convergent. But integral 1 to infinity 1 over square root of x dx and infinity 1 over x dx were both divergent. And you can quickly check this. So there's a very important result. Which is, if you have integral 1 to infinity 1 over x to the p dx, where p is any number, then this is convergent for p greater than or equal to 1. Sorry, greater than 1, which is this one. And it is divergent for p less than or equal to 1. I think I wanted to skip the proof, but I still want to do it because it's just not in my DNA to do this. So I'm just going to say for p equals 1, we already verified. This is done. We already verified this thing. So we have to verify for the other two, which is p is less than 1, p is greater than 1. But before we do that, let's start this integral. So I'm going to take this. So this is going to be integral 1 to b, 1 over x to the p dx, and limit as b approaches infinity. So far, so good?
Quick question.
Sure.
P is convergent. This
The
equation
integral
is convergent for
correct.
P is greater than 1 or P is greater than and equal to 1?
No, equal to 1, you already saw it's divergent. So if you look at the red check there, yeah. And this can be quickly done. You just turns out to be ln x. It's going to be from 1 to b. So you have ln b. But as b approaches infinity, ln b approaches infinity. So this is infinity anyways, which, you can really, really quickly verify because you know the integral of this one.
Got you. All right. Thank you.
Right? No worries. So I'm going to compute this one, which is going to be not the limit part. I'm just talking about the integral, which is 1 to b, x to the negative p dx. So this is going to be x to the negative p plus 1 over negative p plus 1 from 1 to b. So I'm just going to write this in a nicer way. So this is x to the p minus sorry, 1 minus b over 1 minus b from 1 to b. And so this is going to be b to the p minus 1. I'm saying something where I'm writing correctly. Minus 1 to the 1 minus b over 1 minus b. And we are supposed to take the limit as b approaches infinity. So I'm going to pause here again. I want everybody there. So far, so good? And now you would say it's all about the limit. The integral is done here. You already did the integral because this is this. So how do we do the integral? Oh, the exponent goes 1 up. So we went 1 up, divide by the same number. So the integral is done. And we are here right now. So it's all about the limits from here on. Questions? We're okay?
I think I'm fine.
Okay, so let's keep going then. So you would agree with me 1 to the 1 minus b is just going to be 1. So I'm going to write that, but oh, this is limit as b approaches infinity. B to the 1 minus b over 1 minus b minus 1 over 1 minus b. Because all I'm saying is this, if 1 minus b is positive, negative, whatever the exponent you throw at that, it's just going to be 1. So now here where the game begins. So what could be the values of b? So in other words, I'm just trying to say, what if 1 minus b is equal to 0? Oh, in this case, b equals 1, I know it is divergent. And what is 1 minus b? I'm going to say this is the exponent of b. So I'm just trying to go into cases. What if exponent of b is 0? And then we already have that. So what if exponent of b is positive? Oh, that means 1 is greater than p, or p is less than 1. Okay, let's look at that one. So you are saying, and not completely stop writing and just look at this one. So you are saying this is a negative number. Sorry, this is a positive number. I'm sorry. 1 minus b is greater than 0. So this is a positive number. So if this is a positive number, just imagine any positive number there, say b to the 20 or b to the 30, whatever it is. So what happens to this b to the n, for example, where n is positive? As b approaches infinity, what does happen to this b to the positive exponent? What does it approach to?
Infinity?
Very good, Sam. Infinity. So this is going to be infinity minus, but remember this is 1 minus p is positive, so you're just going to have 1 over 1 minus p, which is still infinity, isn't it? So it's going to be divergent. So I'm just saying from here, for p is less than 1, it is divergent. And I'm going to box this, that exponent of b was positive. Well, what if exponent of b is negative? Well, if it is negative, then 1 is less than p, which means p is greater than 1. And I'm going to write that I'm just saying exponent of b is a negative number. So I'm going to copy it down, but we have b to the 1 minus p. So if this is some negative number, say, for example, it is b to the negative 20, then don't we write this as 1 over b to the 20? And my question to you, as b approaches infinity, this number will approach very good current. So this is going to approach 0. So I'm going to come back and say here that if this is negative, so if b to the 1 minus b is negative, so in other words, 1 minus b is negative, then b to the 1 minus p approaches 0. So you're left with what? Remember, this is a negative number as well. So I'm left with the limiting value will just be 1 over negative of 1 minus p, which I'm just going to say is p minus 1. So, but I'm just going to let it roll like that. That's going to be 1 over 1 minus p. But remember, this 1 minus p is negative. Negative of the negative here is going to make it positive, and the answer is going to be 1 over 1 minus p, which means this integral is convergent. Moral of the story, I want you to remember, so here we go. Integral 1 over x to the p dx from 1 to infinity converges if p is greater than 1, CGS is converges, DGS is diverges if p is less than or equal to 1. That is what I want. So if an integral looks like that, I just look at the value of p, and I know whether it converges or diverges. So CGS is converges, and DGS is diverges. Which brings us to the last test for the integrals. And for that, I'm going to give you that one, and then we're going to probably take an example. Ready for the next one then? So no questions here? So the last thing in this section is the comparison property. And actually, I want you to come up with this one. For improper integrals. Joshua, you signed up for the test. I predict that the trajectory that you are on right now, that word is going to be a part of your life. And if you go to graduate school, then there you go. It just gets scary. So it's a comparison. Oh, your book says test. I changed it, Joshua. This one is for you. So it's comparison property, actually a test for improper integrals. So Joshua, I want you to answer this one because this terrifies you. So you should be able to answer this one for me. So, and everybody just stop writing because I'm going to literally draw pictures. So this comparison property is written in a box in the textbook in section 7.8. So I'm going to actually read those lines, and I'm going to start drawing pictures. So the first one, it says, the first thing in the box, it says that f, g are continuous functions. And I do this a bit differently than the book, so please be here. So continuous functions. And what do we mean by that? Oh, no holes, no asymptotes, no breaks. Number 2, f is greater than or equal to g for x greater than or equal to a. What happens before or after, we don't care. So here we go. So I'm going to draw pictures. So remember, they are continuous. They both are continuous functions. So I'm just going to say this. Here we go. So here is f. And I'm going to label it. And here is g. And this is that point A. It doesn't have to be point of intersection. I can draw something where it's not a point of intersection, but this is A. I'm going to keep things simple, so I'm going to change my G a little bit, just because you will see why. So just to make things simple right now. And maybe they don't meet at all after. Sorry. So no kind of assumptions here. So I'm going to come back again, trying to grab my pen. And let's say this is how it goes. So, and Joshua, this one is for you. So when we talk about integral a to infinity f of x dx, what does it mean? So Joshua, go ahead and type it. What does it mean? I want conceptually. I don't want any answer there. And very good. So it is area under the curve. So it's a red function. So I'm just going to say it is, oh, sorry. So I'm just going to say it is this area, right? With the same token, f from a to infinity. So if I go integral a to infinity g of x dx, then that would be this blue area. So it's area under g from f to infinity, a to infinity, sorry. Here's a question for all of you. And so tell me if, and this is a big if, and I like to work with the same thing. So if somehow I knew that area or this integral g of x dx is divergent, what does that mean? Oh, remember we talked about this one, meaning it's an infinite area or the limit does not exist. What can you say about integral a to infinity f of x dx? Is this going to be convergent or divergent? Thank you, Karen. Joshua, how about you? So I will wait for you. So here we go, Joshua. So here is the question. If integral a to infinity g of x dx is divergent, which means it has got infinite area under this blue thing is infinite, then what can you say about the red area, which is under the red curve? So what can you say about that? And that's going to be very good. Now I'm going to start the other way around. Please stop writing, Joshua. Just answer my question. I'll give you time to write, I promise. So now if integral a to infinity f of x dx is convergent, which means what? Oh, it adds up to a finite number. What can you say about integral a to infinity g of x dx? So that means it's finite area. And anybody? Very good. It's convergent. And stop writing, all of you. And now I'm going to flip this and I'm going to say, okay, so what are we saying here? I'm going to go all the way up and I'm going to write it in the picture there. So all I'm saying is, if the little guy, I call this the little guy because G is the little guy. So this is the little one. And this is the big guy. So all I'm saying is, if the little is divergent, then the big guy is divergent. But if the little is convergent, what can you say about the big guy?
Absolutely nothing.
There you go. So thank you so much. So if it is convergent, if G is integral, meaning the blue area is convergent, what can you say about the big guy? Inconclusive. Let's play this game the other way around. What if we know that the big guy, this big guy, is convergent? Then what can we say about the little guy?
It's convergent.
Very good. If you know the big guy is divergent, what can you say about the little guy?
Nothing.
Very good. So this is inconclusive again. This is it. This is your property of improper integrals. Where do we use it? And I'm just going to give you a very quick example, which relates both of these. So here we go. And I think I'm going to summarize this in a table. So f was greater than or equal to g for x greater than or equal to a. And all we are saying is simply this. If integral a to infinity g of x dx is divergent, then integral a to infinity, maybe I should make a table. Hang on, let me just erase this. So this is the premise. They are all continuous. And I'm saying this. If integral a to b g of x dx, if it is divergent, then integral a to infinity f of x dx is divergent. If this is convergent, then this is inconclusive. Can't say. With the same token, now I'm going to start here. The arrows goes this way. So if this is divergent, then this is divergent. Now I'm going to say if this is convergent. Convergent is a finite amount of area. Then I know this is convergent. If this is divergent, can't say. And that is the comparison property. So you're making a conclusion about one integral knowing the other. So I'm going to pause, let you write. Here's an example. Any questions? But this is how I remember. I remember it's the little guy and the big guy. Yes. Which one is the upper and the lower? So Lucas, answering your questions, there are two things you need to know. And I'm glad you asked this. So there are two things you need to know. One is who is greater and who is smaller. And second, which one of these things do you know? Do you know this? Then you can conclude this. If you know this, you can't say. The same relation, but if you know this, if you know something about the big guy, then you can say something about the little guy. So you need to know two things, who is upper and who is smaller, and whose value do you know? Which integral do you know? Which area do you know? Okay. So ready for an example then? And here we go. And I'm thinking you all are ready because nobody's saying anything. So here is an example. Which goes something like this. So I don't know what this looks like, but you are saying area under this curve from 0 to infinity. But it looks like this graph will go from 0 because at x equals 0 is going to take the value 0, and then it's going to be all positive. So I'm just saying because x is between 0 and infinity, because the interval this is always positive. But then here is the thing, it's 0 to infinity, so I know it's an improper interval. If it's an improper interval, I want to know if it's convergent or divergent. So it converges or diverges. That's what I want to know. Now I'm going to have you recall, and that's the connection that you will see in my lectures. That's why I do the problems that I do. We just did, and I didn't even finish that one. I just wanted you to see that. We just did something like x cubed minus 1 dx. And then it was so long to do that integral. So I am just going to, so Karan, you're a little bit ahead of me. I hope you're done that intermediate step and then you're just not writing it. So I'm just going to call this as 0 to infinity. Sorry, I don't want to rewrite too much. So I'm just going to call this f. So here it goes, that f is x over x cubed plus 1. In 0 to infinity, for x greater than or equal to 0, which is another way of writing this, I know, please stop writing and just see what I'm writing here. And as I write, any questions you have. So because x is greater than or equal to 0, I know x cubed plus 1 will always be greater than or equal to x cubed. Agreed? So I'm going to say, take the reciprocal. So 1 over x cubed plus 1 is less than or equal to 1 over x cubed. So multiply both sides by x. Because x is positive, I don't have to worry about changing that sign in between. And now I'm saying, oh, x over x cubed plus 1 is less than or equal to x over x cubed. So this is f, and this is g. So this is the big guy. Sorry, this is the little guy. Sorry. So I make a note, this is the little guy. And this is the big guy, which is 1 over x squared. And now what can I say about integral a to infinity 1 over x squared dx? Well, by that theorem or that rule or that we did that, as you point out, Karan, you're going to say, okay, p equals 2 is greater than 1, so I know this converges. So if the big guy converges, then the little guy, and I'll pause here. So questions. So fill in the blank for me, because the big guy converges. The little guy converges or diverges?
Converges.
Very good. And how do you come from here to here? Oh, you're going to say by the comparison test. So what is the crux here? The main basic idea is you building that G. This is new. You're building that G. There was no G there. So you are sort of looking at this one and you are telling yourself, oh, I do not want to integrate. I just want to first see if it is converges or diverges. If it converges, then I'll bother integrate. If it diverges, then it is something else. But this time, the example that I picked, or the problem it's going to say, is just asking you whether this improper integral converges or diverges. So if I'm just asked that question, then instead of going through the whole motion of integrating, I would rather do this, which is algebra, which means I'm using the comparison test to tell me whether it converges or diverges in the first place. And then if it asks me to compute the integral, of course I have to go compute the integral. So I'm going to say questions. And I'll let you write it. Jonathan, the x cube, that was because, and hang on, that was because of the problem. See, you wanted to know if this converges or diverges. So I looked at this denominator and I said, okay, but x cubed plus 1 has to be greater than or equal to x cubed. So I'm just comparing this with this. I'm getting something to compare it with. So in other words, if this was x to the 5 plus 1, I would have said x to the 5 plus 1 is greater than or equal to x to the 5. So anything, I'm just looking at building on that function. So if it was square root of x plus 1, I would have said, oh, square root of x plus 1 is greater than square root of x.
So if the x cubed plus 1 is greater than x cubed, why is it that 1 over x cubed plus 1 is less than 1 over x cubed?
And for that, I'm just going to take a very simple example, and you should agree this, that 3 is greater than 2, but 1/3 is less than half. Meaning when you take the reciprocal, you switch the inequality. Right?
Yeah.
And then a very important thing, what are the two instances in which we switch the inequality? Once when we take the reciprocal, the other when we multiply by a negative number, because that's when the inequality switches again. And that is why I said that, oh, multiply both sides by x, but I keep writing here, oh, x is positive, so I don't have to switch the inequality, continuous. We have used the comparison test to tell if an integral converges or diverges. So this is the foundation for sequences and series. So you are going to see this again in sequences and series. So I like to do this again. So you see this upcoming again. So when you come back in a week, we are going to go on to sequences and series. And so you're going to see this again. And so you have to get to this idea of building up things. Shall we okay there? So here we go. So I am just going to say maybe one more. And I can't read the textbook. This is where I miss you. Okay. So should we do one more example? I ask stupid questions. So here we go. Integral 0 to pi. I'll let you take this one over square root of x dx. We just want to know whether this converges or diverges. So first things, is it an improper integral? And if it is, why?
I suppose just flipping a coin isn't really a good way of getting the answer.
Well, if the coin lands on heads and your heads has the correct option, then it is.
Huh. Yeah, I think it is an improper integral.
Why? That's where your choice doesn't work. So you're right, it's an improper integral. Why?
Aside from the fact that I didn't think you would not give us an improper integral, isn't it because it's over root x?
Very good. As Lucas answered this, it is discontinuous at 0. So it has a discontinuity. So if we are computing this one, we're going to do all of this, but no, we just want converges or diverges. So we are just trying to build this up. So we do understand that x is between 0 and pi. So 0 is less x is less than pi. So it is that interval. So tell me, in this interval from 0 to pi, what happens to your sine squared x?
It goes from 1 to 0, doesn't it?
Very good. So here is your sine x from 0 to pi, right? So the maximum value it takes is 1. So I'm going to say, oh, 0 is less than or equal to sine squared x is less than or equal to 1. So divide by square root of x. And I get 0 is less than sine squared x over square root of x, less than or equal to 1 over square root of x. And now I wanted to do this because this is a different version of comparison test. So I'm just going to point out that this is the little guy and this is the big guy. So we want to know if this big guy converges or diverges. Remember, this is not 0 to infinity. So no, you do not get to use that, but you get to compute it. So now I want to know integral 0 to pi x to the negative half dx. That means this is going to be limit as b approaches 0 from the right, integral b to pi x to the negative half dx. Which means this is limit as b approaches 0. So x to the negative half is going to be 2 square root of x from b to pi, which is going to be 2 square root of pi minus 2 square root of b. Now take the limit, and I'll wait. The answer is
B approaches 0.
Current pet. You were talking about the limits. Oh, okay. So limit as b approaches 0. I'm hoping, Karan, you're saying that this approaches 0. This quantity approaches 0. So the answer is 2 square root of pi. Thank you. So what does that mean? Oh, it means your big guy, this one, converges. So tell me if the big guy converges, then the little guy. So I'm just going to say by comparison test. I'm just going to say this, that this is, I don't know if you want to introduce F and G. I'm just going to say the big and the little. I really, really like that. What I want you to write, if you want to write big and little, go for it. I'm not going to take points off because you don't write it. I'm not going to give you extra credit because you write it. Or I'm just going to say is by comparison test. What do I know? That integral 0 to pi sine squared x over square root of x is convergent. So it's a convergent integral. So questions. And this is the end of 7.8. So I do want to go into 8.1 today. And then hang on if you could for a little bit, because I'm just going to take maybe 2 minutes of extra time. Karan, I'm going to put it more generally, is what you get is you get the correct inequality. Remember, you need an inequality and you need the correct decision. So you did all this work. But if this was divergent, then comparison test is still inconclusive. It doesn't get you there. But you have to build up the G. You have to build up something to compare your function with. Once you build that up, once you build that relation, who is big and who is little, then you need the right sort of verdict to use the comparison test. So if we don't get the right verdict here, then comparison test doesn't give you any answer. Does that answer your question? And yes, we all you do is solve for the guy you made up because you didn't want to do this one. And this integral is going to be horrible. And we are going to do it, so, but not now. We are going to get to sequences and series and then sort of start doing it. So here we go. So I don't see any questions. So this is the end of chapter 7. And we are going to go into chapter 8. Chapter 8 is applications. Long, long ago, when we were seeing each other, I promised you, you're going to set up an integral. Look how far you've come. You already set up an integral to find area, volume, average value, work done. Add to this one. You're going to this list, we're going to add arc length, surface area, and some physics, which is force due to fluid pressure, and centroid. But right now, we are just going to go with arc length. Yes, Joshua, you are right. If the little guy was divergent, then the big guy is divergent. But again, the same thing. What I'm trying to say is this, that if the little guy is convergent, then you can't say anything about the big guy. So you need the right relationship between the two functions and the right verdict to go with it. And did I answer that question, Joshua? So just let me know. Okay. So stop there and just watch. We want to compute the arc length. So here we go. I'm going to set it up. Just watch this. You know, I put up the notes anyway. So here's the idea that y equals f of x is that curve from A to B. And yes, it's a continuous curve. So I'm just going to draw it. Here we go. And this is x equals A, x equals B. What do we want to find? Oh, we want to find the length of this, which is the arc length. I'm going to give you a kind of visual just to imagine this one. So if you are going to watch, so we are Americans here, we're sitting here, and we are watching this Soviet satellite move from this location, which was right here, to this location. And we want to know exactly how much distance did it travel. And so for that, what are we going to do? We're going to set up an integral. Why do we set up an integral? Oh, we set up an integral because it's not a straight line. It's got this curvy path. That means f is changing. I drew this for a reason like that a little bit, but you can imagine this one to be doing these kind of maneuvers as well. So you want to know the length of this one. So whenever things are changing, what do? Oh, first we chop it up. So I'm going to divide AB into n sub-intervals. So I'm going to say, okay, this is P naught. This is P1, P2, P3, and so on and so forth. So I'm saying P naught is x naught, y naught. P1 is x1, y1. P2 is x2, y2, and so on and so forth. That means what we have been already doing. So AB into n pieces. Again, I'm doing this a little bit larger pieces. You know these pieces get smaller. So this is x0 to x1, x1 to x2, x2 to x3, and that one is y3. I'll be okay there. So I'm going to assume this is okay. So I'm just going to grab one piece. So one piece, which is from P0 to P1. So I'm going to approximate the length from P0 to P1, which is actually the distance, P0 to P1. But yes, I'm going to approximate this one. I'm going to approximate this, what you see there, by a line, by this straight line. So I'm approximating the curve by the line. Why? Because I know the distance formula. So I'm going to say length of P0, P1 is, of course, an approximation, square root of x1 minus x0 squared plus y1 minus y0 squared. And I want everybody here. So far, so good. And I'll let you write or I'll let you see, but go ahead and type in if you're ready. So we ready then? Great. And now
yeah, I guess.
Okay, so I'm going to come back to the picture. So again, we are approximating this one by this line, and then you know all of this stuff, that how will this approximation, how do I make it better? Oh, I have to make the interval smaller and smaller. So I'm going to write that. So if I make those intervals smaller, then the line approximation just gets better, isn't it? What do I mean by that? I mean, look at the proportion. We are so little. The earth is supposed to be round, but we still have straight roads. Everything doesn't just curve for us. That is what I'm trying to say here. More importantly, here we go. Again, stop writing. So I'm saying, okay, this x1 minus x naught, isn't this x1 minus x naught? So I'm going to pull that out. Isn't this x1 minus x naught? With the same token, isn't this y1 minus y naught? So tell me, what is x1 minus x naught again? Remember, you divided into n subintervals, so I'm going to say, isn't x1 minus x naught delta x? Isn't y1 minus y naught delta y? So now I'm saying, oh, that length between just 2 points, p0, p1, just one piece, is going to be square root of delta x squared plus delta y squared. So far, so good, Pickle. After this, I'm going to take algebra. So I'm going to pause in a little bit. I just want questions. After all, you're just going to remember the formula, yes, but you have to know where things are coming from. So no questions then? We're okay? So I just want one yes from someone. Great. So now time for algebra. It always was. So I'm just going to say, can I write this as? And please do not write this. Just follow along. So can I write this as? So I'm going to say, can I write this as? And can I write this as? I'm going to have this, pause it a bit. Are we okay here? Because I want to go back to the picture. Current, that is in the picture. So here, if I go up here, which I wanted to do anyways. So this was x1 minus x naught, which was your AB into intervals, right? And so it is delta y. With the same token, I called y1 minus y naught to be delta y, and the other one was delta x. Oh, sorry, your question was delta y over delta x, because here I took this out as a common factor. So my intention is that when you distribute it, you get this back. So does that answer your question? Aaron, you said something, I have no idea what that means. What does that caret mean?
I think it's same as above.
Oh, okay. Okay, so Aaron, did I answer your question then? Did you get that as well? And everybody else there. So Aaron, point out to me what it is. What is it that you sort of are not getting? And you can say it. You don't have to type.
So my question was, how did you get y over x? Because you said you distribute it, course.
No, I'm just saying, okay, maybe I should do this backwards. So that was to Karan's question. To you, I'm just going to say I'm going to factor out the first quantity, which is delta x squared.
Oh, okay. Okay,
Yeah,
I
and
see.
then
Yeah.
and then my explanation was that, why do I have this quantity here? Because when I distribute it, I get this back.
Okay.
So it's just a way of how
Okay.
you want to see
Yeah.
it. So yeah. So if you're
Okay,
okay,
now I see it.
okay, great, we're here. So I'm assuming everybody's here. Again, as I said, drop your pencils. I'm going to go all the way back up there. And now I want your last semester. Last semester, you did. And I'm just going to take this and draw it down here. So here's where we are at. You said this is P0 to P1. You said I'm going to approximate this length by the length of this line. So we are approximating this one with this one. Then you agreed with me that this is delta x, this is delta y. Here's where we began. I'm going to say here was your x-axis, this was your x0, this was your x1. I'm going to remind you this was x0, y0, this was x1, y1. Your function is continuous. It is a closed interval. So last semester, extreme value theorem said what? Oh, sorry, not extreme value theorem, mean value theorem, which I know we did. And you know who you are when I'm saying this. So we did the mean value theorem, which said what? That if you have a closed interval, and if a function is continuous, then there is at least one point in here so that the tangent here is parallel to the line joining the ends. How does it apply here? Well, delta y over delta x is the slope of the red line. So I'm saying there is a xi star, I'm going to call it x1 star, such that what? F prime at x1 star is delta y over delta x. Where is this coming from? From the mean value theorem. And I'm just going to go back and come back to the questions. Actually, I'm going to finish this and take questions. So I claim there is an x1 star in each of these intervals. In each of these intervals, you have that. Here is the line joining. Here is the value. Here is the line joining between x2 and x3. Here is the line joining. Well, here is the value. So I claim this is in every interval. And then we are saying what? Length is limit as n approaches infinity, which means delta x approaches 0. Of what? Of delta x square root of 1 plus f prime of xi star squared. And I goes from 1 to n. So I'm just going to say this is the Riemann sum. Because your summation, I'm going to write it a bit more carefully. So this is going to be Riemann sum. So length is going to be integral a to b square root of 1 plus dy by dx dx. And that's the formula I really, really need from you. That's the formula I want you to remember. I want to do an example, but if it doesn't happen, it doesn't happen. But I'm just going to go back, and all of you, please stop writing and look at this one. So I'm going to clean this picture a little bit. So I'm going to clean this fluff. And I'm going to just draw that curve. So you are saying length of this one from A to B is integral A to B square root of 1 plus dy by dx squared dx. But this is the American vintage point. And what I mean by American, Houston is watching, the Soviets like go by, but at the same time, now let's flip the tables. So the Soviets are watching, Putin is watching, and it's the American satellite this time that goes from here to here, which means C to D. So can you tell me, we're going to play the same game, we're going to divide this into little pieces. So each one of these is going to be approximated by a straight line. So tell me what the integral would be. The other form would be length is integral from, anybody?
Length equals integral A to B square root of 1 plus dx over dy squared dy.
Oh, I loved it. You just missed one part, which is C to D, because Y is between C to D. But you got all the other parts for me. Thank you. Because here, I'm just going to write comments. Oh, X is between A and B. And we are integrating with respect to dx. Here, Y is between C and D. And we are integrating with respect to dy. So, do we have time for an example? Should we do an example right away, or are you okay? That means I'm just asking you, are you ready to stay for an example? Or so the first thing I'm going to do is I'm going to have the due date for this particular homework. I'm going to change it to the Monday after the break.
Sounds good to me.
Okay, so a quick question. Do you want to see an example before you leave? Or you have to leave and go to your other class? So just about, okay, then let's do a very quick example. I'm going to do a very quick one. It's not going to be bad, but it'll give us. So here it is. Y equals 1 plus 6 x to the 3 halves. 0 is less than x is less than or equal to 1. And it says find the length of the curve. Obviously from 0 to 1. So I don't know about you, but I'll divide this into two. Divide the page into two parts for this kind of thing. So here we go. So I divide this. On one part, in one part, I set up the integrals. So the length is going to be integral 0 to 1, square root of 1 plus dy over dx squared dx. Why this one? Because I noticed that x is between 0 and 1. I also note that y is a function of x. On this part, I get ready. This part I call getting ready. So now I start, okay, y equals 1 plus 6x to the 3 halves. So dy by dx is just going to be 6 3 halves x to the half. Remember, we are doing the derivative now, which is really dy by dx is 9 square root of x. I'm patching to the formula here, so I'm supposed to square this, so this will be 81x. And so I come back here and say, okay, this is integral 0 to 1 square root of 1 plus 81x dx. Everybody there?
Yep, makes sense to me.
Great. So now we just have to integrate. So tell me, what would we use? So I'm just going to say, still, because I'm taking this time from here, u equals 1 plus 81x. So du over dx is 81. So I'm going to say dx is 81 over du. So I'm going to have this one and this one. And this is done now. So this is going to be empty box to empty box, unless you want to change it. And we are going to have square root of u times 81. Sorry, I messed this one up. Du over 81. So sorry about that. So du over 81. Right?
Yeah.
And so this is going to be 1 over 81. And then a little trick which you will enjoy in this section. So you know this is 1 over 81, 2/3, u to the 3/2 from empty box to empty box. So this is 2 over 343. 1 plus 81x from 0 to 1. Here is my trick. And I think I've shown you this before. X to the 3/2 is x square root x. What do I mean by that? This is what I want from you, 343. So you are going to say, okay, this is 82 to the 3/2 minus 81 to the 3/2. Use the trick. It should be, oh, it's 243. Thank you. So I'm going to change that. So this is 243. And so we have 2 over 243. Now I'm going to go 82 root 82 minus 81 root 81. Now call out the mistake. I thought somebody would see it. So this should have been, right? Thank you. Great. So that's it. It's 2 over 343. 243. I'm obsessed with that. And that's the last example of the day. And there are some nasty bits in here, but I want to show you the one more algebra thing that I would like to run by you. Not today, don't be scared. I want you to start your break. I know you have work to do. So here's what I'm going to do. The homework that I'm assigning today, whatever that number is, will be due Monday after the break. But there is a quiz that I already assigned, which is due March 30th midnight. Which is 7.4. And officially the class is